3, video lecture number 31 on curl and divergence. Now we've seen how the differential operator del can be applied to a function f and it yields a vector. Next, we're interested in seeing how it can be applied to a vector field where this vector field f has components p, q, and r, and the partials of p, q, and r must exist. And we're going to see two ways in which this can be done. One way gives or yields a vector, and the other way gives us a scalar function. So here's our definition. The curl of f is equal to del r del y minus del q del z I hat, so that's the x component, plus del p del z minus del r del x, plus j hat, plus del q del x minus del p del y k hat. An alternate way to remember the curl is that the curl of f is equal to our differential operator crossed with f, our vector field. And if you need to remember, del, your differential operator, had components del del x, del del y, del del z. And so let's take this cross product here. So we'll have I hat, j hat, k hat in the top row, then del del x, del del y, del del z in the second row, and then f had components p, q, and r. So notice when we compute this determinant here, so for the first component I'll have del r del y minus del q del z, which matches exactly with our definition for the first component, okay? And then you can verify that the rest follows suit. So for the next component, you would have del p del z minus del r del x. Yep, looks good. Del p del z minus del r del x. And then last component will be del q del x minus del p del y. All right, so pretty straightforward. If you remember that the curl of a vector field is equal to differential operator crossed with that vector field, then you won't have any problems. So let's go ahead and apply the definition. Find the curl of f for the given vector field f with components cosine xy, sine xz, and xz squared. All right, so here is how I recommend setting up your determinant. Write out the bottom row with the vector field first. That way you know your spacing is appropriate. And xz squared, and then just work your way up. So you'll have del del x, del del y, del del z, and then I hat, j hat, k hat last. Okay, so let's go ahead, see what we got. So expanding along first column, first row, I'm going to take the partial derivative of xz squared with respect to y. Well, that's just going to be 0. Minus partial derivative of sine of xz with respect to z. So I have to apply the chain rule and multiply by x. So I'll have x cosine of xz. So far, pretty easy. Let's move on to the next column. So I'm going to take the partial derivative of cosine xy with respect to z. Well, that's going to be 0. Minus partial derivative of xz squared with respect to x. Well, that's just going to be z squared. And then let's move on. Last one. We're going to have partial derivative of sine of xz with respect to x. So by the chain rule, I'm going to have to multiply by z. And then I'll have cosine of xz minus, and then now I'm going to take, this way, partial derivative of cosine xy with respect to y. So I'll have negative sine xy, and then by the chain rule I have to multiply by x. So this will be plus x sine xy. Okay, and then I can just clean it up and write it as negative cosine xz, negative z squared, and then z cosine xz plus x sine xy. And that's it. Okay, well, you're probably wondering, what is curl? What does it mean? What does it represent? Well, one interpretation of curl has to do with rotations in a fluid, where F represents the velocity field in the fluid flow. So the curl of F at some point P, so we'll say P has coordinates x, y, z, that measures the tendency of the fluid to rotate. At that point in space, basically. Now, if you take the magnitude of the curl, so the length or magnitude, because remember, curl is a vector, that gives the speed of rotation. Also, the fluid rotates about the axis given by the curl of F. And lastly, if the curl of F is equal to the zero vector, all three components are zero, then we say F is irrotational. Not rotating. Okay, so pretty straightforward. Now, this brings us to the following theorem. It states that if F is a function of three variables, okay, so we have a function of x, y, and z, and it has continuous second order partial derivatives, so F is C2, then the curl of the gradient of F is equal to the zero vector. Okay, let's go ahead and prove it. It's a really direct proof. You just apply the definition. So I want to find out the curl of the gradient of F. So I'm going to take the cross product of the gradient of F, which is partial x, partial y, partial z, with our differential operator. So del x, del y, del z, I hat, j hat, k hat. Okay. So notice here, for our first component, I'm going to take the partial derivative with respect to y of the partial with respect to z. So that would be f partial zy, correct? Minus, and then here, this product, that's going to be the partial derivative with respect to z of the partial derivative with respect to y. So that would be partial yz. Make sure you get the order correct. Okay, let's move on. Next entry, we'll have partial of x, and then differentiate that with respect to z. So that's partial xz minus, this would be partial zx. And then lastly, here we go, we'll have partial yx minus partial xy. Now remember, one of the necessary conditions for this theorem was that f had to have continuous second order partial derivatives. And since this is the case, we know that partial zy is equal to partial yz, partial xz is equal to partial zx, and partial yx is equal to partial xy. Do you remember the name of the theorem that told us that? Comment down below if you do. Anyways, since the mixed partials are equal, that means each of these components now is going to equal 0. So we're going to be left with 0, 0, 0, which is the zero vector as desired. All right, so that proof was really straightforward. Now, we've already seen that if f is a conservative vector field, that means that it's equal to the gradient of some potential function f, a function of several variables, typically 2 or 3. This also means that if f is conservative, then the curl is going to be 0. Why is that? Well, if f is conservative, then the curl of f is equal to the curl of the gradient of some potential function, which we just showed is equal to the zero vector. So here's a fact: the curl of a conservative vector field is 0. All right. So what does this mean for us? Well, if we find the curl of some vector field and it's not equal to the 0 vector, then we know our vector field is not conservative. However, in order to use the curl to test whether f is indeed conservative, right? So it's easy to show that it's not, but if we want to check that it is, then we have to impose additional conditions. So first one, yeah, it has to satisfy that the curl of f is equal to the 0 vector. And this is actually equivalent to checking the pairs of partials that we did previously. Remember, before we've tested whether or not vector fields were conservative, and we had 3 conditions to check. The first one being that the pairs of partials, those mixed partials, were equal to each other. And that's the same thing as checking as if the curl of f is equal to the 0 vector. Then the next condition that has to be satisfied is that P, Q, and R have to have continuous first partials. So they have to be C1. Can you guess what the third one's going to be? It's the same condition as before. So the domain D of your vector field has to be open and simply connected. All right, so notice here in the directions, they tell us for the following example, use the curl to determine whether or not the following vector field is conservative, and then if it is, go ahead and find the potential function. So since they're telling us to use the curl, then I'm going to use the curl to verify the first condition, and I'll check the other 2 same as we did before. All right, so to help us out, I'm just going to label this is P, this is Q, this is R. All right. And we're going to go ahead, let's compute the curl of f. So remember, put your vector field in the bottom row first. So z, 2yz, and then x plus y squared. Then the differential operator, so del x, del y, del z, and then I hat, j hat, k hat. All right, here we go. So we're going to have partial derivative of x plus y squared with respect to y. That's going to be 2y minus partial derivative with respect to z of 2yz. That's 2y again. So far, it looks like we're in good shape. Let's move on. Partial derivative with respect to z of z, that's 1. Minus partial derivative of x plus y squared with respect to x, that's 1 also. Okay, and then last component, partial derivative with respect to x of 2yz. I don't see an x, so this is constant, that's 0. Minus partial derivative of z with respect to y, yep, that's 0 again. So yay, first condition satisfied, we get the 0 vector. All right, let's see if the second condition satisfied. P, Q, and R, let's look at them. Do they have continuous first partial derivatives? Yes. I can't just say that without justifying myself. I know that because they are polynomials. We have a theorem that tells us that. And then lastly, what's the domain for our vector field? Well, it's all of R3. Make sure you identify it correctly, which is indeed open and simply connected. No problems there. So what does that tell me? That tells me my vector field F is conservative. All right, so now they want me to find the potential function. Well, remember, P, that's my partial with respect to x of the potential function. So that equals z. And then partial with respect to y is q. So that's 2yz. And then the last component r is the partial derivative with respect to z of our potential function. So let's just go backwards and anti-differentiate accordingly. So if the partial with respect to x of the potential function is z, then that means f is equal to xz plus possibly some function of y and z, right? Which would just be a constant and go to 0 when I differentiate. So I'll call that g of xz. Similarly, I'm going to anti-differentiate the next component with respect to y. So my potential function would have the form y squared z plus some h of just x and z. And then lastly, I'm going to anti-differentiate with respect to z. So the potential function would have the form xz plus y squared z plus some other function, let's call it m of xy. So I'm going to put it all together. So I've got xz. All right. So my potential function f of xyz has xz in it. Plus, let's see here. Well, y squared z, that's that next term that's appearing. Y squared z. And I think we have everything accounted for, yes? Okay, so there's our potential function. And that's all we do with it for this particular problem. All right, very good. Moving on to the next idea, we're going to look at divergence. So, by definition, the divergence of a vector field F is equal to del P del X plus del Q del Y plus del R del Z. So notice here, since we're adding each of these partial derivatives together, our end result is a scalar function. So this is not a vector the way curl was, this is a scalar. And remember, F had components P, Q, and R. And another way to remember the formula or definition for divergence is that the divergence of F is equal to your differential operator del dotted with your vector field F. Remember, our differential operator has components del del X, del del Y, del del Z, and then I dot that with F, PQR. And so I'm going to end up with taking the dot product, del P del X, plus del Q del Y, plus del R del Z. Easy as that. Okay, so ready for something cool? Neat little way to remember it. When you're computing the curl, I want to write this nicely for you people. When you're computing the curl, you take a cross product. So you take differential operator, cross it with F, and it gives you a vector. Just like when you take the cross product of two vectors, you get another vector. If you need to compute the divergence, you take a dot product. So you take the differential operator, dot it with your vector field, and that gives us a scalar, just like when you take the dot product of two vectors. Beautiful. All right, so let's find the divergence for the following vector field, F, with components sine of x, cosine x, and z squared. This is going to be so relaxing, look. So divergence of F is going to equal, so partial derivative of sine of x with respect to x, that's cosine x, plus, now I take partial of cosine x with respect to y, that's just 0, plus partial of z squared with respect to z, that's 2z. So that's it, it's just cosine x plus 2z. Box it and move on with your life, if you can. All right, we're going to put a cloud around it since it wasn't cooperating. Very good. I feel like it's time for another theorem. Are you ready? So if F, our vector field, has components P, Q, and R, so it has to be a vector field in R3, and P, Q, and R have continuous second order partial derivatives, then the divergence of the curl of F is equal to 0. And notice this 0 is not bold, right? It's a scalar quantity since I'm taking the divergence. All right, let's do the proof. We're just going to apply the definition directly and it's going to work itself out, watch. So we want to compute the divergence of the curl of F. So this is going to equal our differential operator dotted with the curl of F. Okay, so we have differential operator dotted with, remember, curl of F is differential operator crossed with F. All right, and I'm just going to refer to the definition that we had earlier so we don't have to do this all from scratch. Remember, F F has components P, Q, and R. Okay, so I'm going to replace this with the definition that we had on the very first page. So we have del dotted with Ry minus Qz, Pz minus Rx, and then Qx minus Py. And then now I'm going to take the dot product, so I'm going to differentiate this first component here with respect to x, right? So I'll have Ryx minus Qzx plus, since this is a dot product, now next component I'm going to differentiate with respect to y, so I have Pzy minus Rxy plus, and then the very last component I'm going to differentiate with respect to z, so I have Qxz minus Pyz. And then, just like before, Ryx is equal to Rxy because all P, Q, and R have continuous second order partials. And then similarly, let's see, we're just going to have a bunch of cancellations. So Qzx, this negative Qzx is going to cancel with Qxz. And then lastly, Pzy is equal to Pyz. So those will also cancel out. So I'm left with 0, a scalar, because Ryx is equal to Rxy, Pzy is equal to Pyz, and Qxz is equal to Qzx, since P, Q, and R are C2. Okay, and we finished the proof. Good. Well, let's see how we can apply it. Use the theorem stated above to show that there cannot be a vector field G defined on R3 with P, Q, and R having continuous second order partial derivatives for which the curl of G is the following: YZ, XYZ, and XY. Well, they're telling me to use the theorem above. And the theorem above tells me that the divergence of the curl of some vector field is going to be 0, as long as it satisfies all the necessary conditions. So let's go ahead and take the divergence of, this is already the curl, right? This is not the vector field. They're giving me the curl of the vector field. So divergence of the curl of this vector field G in question is going to equal differential operator dotted with YZ, XYZ, XY. Okay, so take the partial derivative with respect to x of YZ, that's 0, so far so good, plus, now I'm going to take the partial derivative with respect to y of XYZ, well that's XZ, plus, and then partial derivative with respect to z of XY, that's 0, but notice I'm still left with XZ, which is not 0, and that contradicts the theorem. So this is a contradiction. So what does this mean? No such vector field G with the curl that was given to us, with the curl of G as defined, can exist. So whatever they made up and gave us in this problem, it was total garbaggio. All right, aren't you curious what divergence represents? Yes, I would be too. So the divergence of a vector field at a point x, y, z, again, in the context of fluid flow, it measures the tendency of the fluid to leave the point. Or basically to flow away or diverge from the point, hence its name. Okay, so how exactly to interpret it? So if the divergence of your vector field at some point P is positive, greater than 0, that means the fluid is flowing away from that point. So you have a source. If the divergence of your vector field at some point P is less than 0, negative, then the fluid is flowing towards that point. So you have a sink. And then last possibility is if the divergence of your vector field at some point P is 0, then we say that it's incompressible. Okay. Now, one surprising aspect of curl and divergence is that they provide us useful alternate forms for Green's theorem. So you might think, how in the world are they related? Well, here's Green's theorem stated again, just in case you needed a refresher. So C is a positively oriented, piecewise smooth, simple closed curve. D is the region it contains. P and Q have continuous first partials. Remember, we're able to compute the work. Yes, this represents work. So the work as a line integral, or using Green's theorem, we compute it as the double integral, right? Where D is the region contained by that closed curve C of del Q del X minus del P del Y dA. All right, so how am I going to relate this theorem to curl and divergence? You'll see right now. Now remember our definition for work, the line integral over C of P dx plus Q dy was the line integral over that closed curve C of F dotted with dr. And we first kind of came up with this idea because we said, well, we wanted to sum up our vector field, all of that force in the direction of motion, meaning we wanted its projection tangent to the curve. So we had F dot T ds. That gave us the tangential component of F along our curve C. So here we're looking at some curve. It's lying in the XY plane. So right now we're actually in 2D. So my vector field F would have components P, Q, and 0, right? And then we have our closed curve. We wanted to find the work done. And so if you want to review the discussion, that's from a previous video. But we wanted to sum up the work, the tangential component of F along C, which is why we found the vector projection, right, of F along our tangent, unit tangent T. Okay, well, let's take the curl of F. And right now I'm working with F that has components P, Q, and 0, okay? So the curl of F is gonna be, so last row is P, Q, 0. And then I have del X, del Y, del Z, I hat, J hat, K hat. Okay, so let's see, first component's gonna be 0. Yes? 0. There's no Z's going on, so partial with respect to Z is gonna be 0. Very good. Next component, let's see here. So this is gone, this is gone, this is 0. Again, F is just going to involve X and Y, right? Since we're only in 2 space right now. XY plane, so that's going to be 0. And then lastly, here's my Q. We're going to have, and this should look familiar, del Q del X minus del P del Y. Ooh, that looks like the expression in Green's theorem, except for the fact that this is just a component in a vector, right? So how would I make it a scalar? Well, I could take the curl of F and then dot it with K hat, right? Our unit vector 0, 0, 1. So if I take 0, 0, del Q del X minus del P del Y, and I dot it with 0, 0, 1, now I get the scalar del Q del X minus del P del Y. Ooh, so this is exciting. Therefore, the work on any closed curve f dot dr by Green's theorem was equal to the double integral over d of del Q del X minus del P del Y dA, which I could write as double integral over d of the curl of f dotted with K hat dA. Okay, very good. So that's just an alternate way of expressing Green's theorem involving curl. I also promised you that we could involve divergence somehow. Well, in order to get divergence in the mix, we need to consider the normal component of f. All right? And in this case, I'm going to consider the line integral on some closed curve C of f dotted with n, the normal component ds, where n is the outer unit normal. So how would I figure out exactly what that outer unit normal is? Well, remember, you have some closed curve C, it's in the xy plane, and assuming we can parameterize it, that means I can write my curve C as some r of t with components x of t, y of t, and then the z component would be 0, right? And then we have this unit tangent t traced out along the curve, and k hat, that's that same special unit vector 0, 0, 1 from before. Well, if I take the cross product of t and that vector k, t crossed with k will give me n, my outer unit normal. So n is equal to t crossed with k hat. How do I know it's a unit vector? Well, t, remember, that's r prime divided by magnitude of r prime, and k is also a unit vector. I can express t as 1 over magnitude of r prime times dx dt, dy dt, and then 0 in this particular case for our curve in the xy plane. And then now let's figure out what n would be specifically. So n would equal t crossed with k hat. So since 1 over magnitude of r prime is just a scalar, I'm going to pull it outside of the cross product and multiply at the end. So 1 over magnitude of r prime times, let's see here, so we have I hat, j hat, k hat. Next row is going to be t, so that's dx dt, dy dt, 0. And then k hat has component 0, 0, 1. All right, very good. And then if we take this cross product, I'm going to have 1 over magnitude of r prime. Let's see, what are we left with? So this is going to be dy dt minus 0. And then next component is going to be 0 minus dx dt. And I obviously know z is going to be 0, right? Since we're just working in the xy plane. So I'll just leave it as a vector with 2 components. All right? Now, if you'll recall, ds, that's our little increment of arc length, that's equal to magnitude of r prime of t dt. And so I can go back to that vector, or excuse me, the integral that we talked about over our closed curve C, f dotted with n ds. And I can write that as line integral over C, f was pq. Dotted with, I'm going to dot it with n. I have n right here. Okay, so that's going to be 1 over magnitude of r prime dy dt negative dx dt. And then this ds here, I'm going to replace it with magnitude of r prime of t dt. Okay, I'll switch colors so you know this is magnitude r prime of t dt. Good, well, what do you notice we can do? Well, I see this magnitude of r prime is going to cancel out here. Okay, so let's go ahead. Now we can take that dot product. So I have pq dotted with dy dt negative dx dt dt. And then this gives me line integral over a closed curve C of, let's go ahead, take that dot product. I'll have p dy minus q dx. Okay, now pretend you're given this line integral and then now you want to apply Green's theorem. Okay, let me rearrange it so it looks more familiar, that you're ready to apply Green's theorem to it. So you would have negative q dx plus p dy. So think of this negative q as your normal p, and then think of this p as what q used to be. Okay, so if I were to apply Green's theorem now, I would change this to a double integral over d. I take the partial derivative of that component with respect to x. So I would have del p del x minus partial derivative of negative q with respect to y. So that's going to be plus del q del y dA. And my goodness, what is this expression right here? That's the divergence of f dA. Ooh, so therefore, line integral over c of f dot n ds can be expressed as the double integral over d of the divergence of f dA. Very good. Now remember, this line integral here, this does not represent work. That's f dotted with dr. This represents something else. We'll discuss that more later on, but just interesting the fact that Green's theorem can be rewritten and expressed using curl and divergence as follows. So stay tuned. Don't forget to like and subscribe. That helps support the channel. And we'll talk about parametric surfaces and their areas in the next video.